Okay, let's get right into it. Welcome to this explainer, where we're going to completely demystify the complex mechanics of project scheduling and turn it into an easy-to-follow masterclass. Look, whether you're managing a massive software rollout, planning a heavy construction job, or just trying to organize a really complex event, mastering the flow of tasks is exactly what separates a chaotic, stressful project from a perfectly executed one. So today we are breaking down a technique that takes the guesswork entirely out of your timelines.
Let's kick things off with a crucial question, one that pretty much every project manager loses sleep over at some point. How exactly do you guarantee a project finishes on time? It's not just about telling your team to work faster, right? It's really about understanding the invisible underlying structure of your project's dependencies. When you finally know which specific tasks mathematically control your deadline, you suddenly have the ultimate leverage.
So here is our roadmap for today's explainer. First, visualizing with arrow diagrams. Second, defining the critical path method. Third, calculating the forward pass. Fourth, calculating the backward pass. And finally, finding float and the critical path.
All right, Section 1, Visualizing with Arrow Diagrams.
The very first step toward building a viable schedule is just getting organized. You literally cannot manage what you can't see. Visualizing the sequence of events is what allows you to drive efficiencies while still actually hitting your time frame. We always start by creating a simple table outlining tasks, their predecessors, and their durations. Take a look at this example of building a deck. Check out the columns. We've got our tasks, the immediately preceding activity, or IPA, and the duration. For instance, you can't get the permit, which is task C, until you fully completed task B, making the plans. And getting that permit? Well, that's going to take 14 days. This table right here is basically the raw DNA of our project.
Now, what's really fascinating is how we can translate that raw tabular data into two totally distinct types of diagrams: activity on node and activity on arrow. Both of these completely achieve the goal of mapping out dependencies, but they approach the visual layout just a little bit differently.
Notice how on the left diagram, the activity on node, the activities are represented by the boxes themselves, and they're stacked vertically when they happen simultaneously. So tasks C and D happen at the exact same time. But the right diagram, the activity on arrow format, uses the actual arrows to represent the activities. The length of those arrows is drawn to scale to represent duration, while the nodes are really just connection points. For the math we're about to do, we're going to focus strictly on the node-based logic.
Moving right along to Section 2, defining the critical path method.
To figure out the absolute minimum project duration, we have to find the longest sequence of dependent tasks. Essentially, we're hunting for the bottleneck of your entire operation. But before we crunch any numbers, let's get our terminology straight. First up is early start, or ES. It's exactly what it sounds like, the very earliest time a task can begin without breaking any dependencies. If it's the very first task out of the gate, its ES is 0. But if it's a task deeper in the project with multiple preceding tasks, its early start is strictly dictated by the maximum early finish of all its predecessors.
Next is early finish, or EF. This one is super simple. You calculate it just by adding the duration of the task to that early start number we just talked about. So if a task starts on day 5 and takes 3 days to complete, its early finish is day 8. It's a very straightforward, forward-moving kind of logic.
Okay, now let's flip our perspective and move backwards. Late finish, or LF, is the absolute latest a task can finish to not delay the whole project. For the very last task in your project, this is going to perfectly match its early finish. But for everything else, it's determined by looking ahead to the tasks that follow it. Specifically, you take the minimum late start of all its successors.
And finally, late start, or LS. You find this by taking that late finish date and subtracting the task's duration. So if a task absolutely must finish by day 10, and it takes 3 days to do, its late start is day 7. If it starts even a minute later than day 7, the entire project is going to be late. No exceptions.
All right, Section 3, Calculating the forward pass.
Armed with all those definitions, we are totally ready to perform our first analysis without worrying about resource constraints. This is the forward pass. This pass is going to tell us the absolute fastest we can possibly finish this project. The crucial thing to remember is that we must always follow two sequential rules when moving forward through our network. First, find your early start by taking the maximum early finish of all predecessors. We take the maximum because, logically, a task cannot begin until all required preceding tasks are completely finished. Then, step 2, simply add your duration to find your early finish.
So, let's actually apply those rules to tasks A through E and piece together this forward pass table, going row by row. It's like a giant puzzle. Task A starts at 0, takes 2 days, and finishes at 2. Easy. Task B depends on A, so it starts at 2, takes 4 days, and finishes at 6. Task C also depends on A, so it starts at 2, takes 3 days, finishes at 5. Now task D. This one's a little tricky. It needs both B and C to be done. B finishes at 6, and C finishes at 5. We have to take the maximum. So D absolutely cannot start until day 6. It takes 2 days, finishing at 8. Finally, task E depends on D. Starts at 8, takes 1 day, and finishes on day 9. And there it is. That 9 is our final minimum project duration.
Which brings us to section 4, calculating the backward pass.
Now that we know for a fact our project takes 9 days, let's find our late dates. This is going to expose exactly where our schedule has some flexibility and where it is completely rigid. We're just going to reverse our logic here. We start from the end of the project and subtract task durations to find when tasks must absolutely begin. When moving backward through multiple paths, remember we take the minimum late start of the successors to be our late finish. We have to be conservative here to protect that final 9-day deadline.
Let's trace our steps backward from task E at day 9, just subtracting durations until we get all the way back to task A at day 0. Task E finishes at 9, minus its 1-day duration gives it a late start of 8. Task D feeds into E, so it has to finish by 8, minus its 2-day duration gives it a late start of 6. Now task D is the successor to both B and C, so both B and C inherit a late finish of 6. Task B's late start becomes 2, while task C's late start becomes 3. Task A feeds into B and C. We take the minimum of their late starts, which is 2, so A must finish by 2, minus its 2-day duration means it must start at day 0. Boom. The math works out perfectly.
Let's bring it all home with section 5, finding float and the critical path.
With both of our passes complete, we arrive at the final puzzle of our masterclass, identifying exactly which tasks cannot be delayed. We've gathered 4 crucial data points for every single task, and comparing them reveals the whole story. We do this by calculating float. Float basically represents the flexibility a task has. You find it by subtracting early start from late start or early finish from late finish. Either equation gives you the exact same number. If a task has float, great, you have some breathing room.
But if a task's float calculates out to exactly 0, it means there is absolutely no flexibility, literally none. That task is critical. A delay of even 1 single day on a 0 float task will definitively delay your entire final project delivery by 1 day.
Looking at our combined float table, we can clearly see the contrast. Task C has 1 day of float, but tasks A, B, D, and E all have 0 float. Look really closely at task C. Its early start is day 2, but its late start is day 3. It could start on day 2 or day 3 and the project would still perfectly finish on day 9. That's what float looks like in reality. But look at task B. Early start is 2, late start is 2. 0 float. It is rigid.
Because they have 0 float, any delay in tasks A, B, D, or E delays the entire 9-day project. That sequence right there is our critical path, A to B to D to E. These are the specific tasks you, as the project manager, must monitor with absolute intensity. If someone working on task C gets sick for a day, you're fine. But if someone on task B gets sick for a day, you need to pull in extra resources immediately or you are absolutely missing your deadline.
So, now that you've mastered the underlying mathematics of scheduling, it's your turn. Can you apply these exact same equations to find the critical path of this new 8-task project? Grab a piece of paper, map out your nodes, run your forward and backward passes, and hunt down that 0 float. Once you can reliably do this, I promise you'll never look at a complex project as a chaotic mess of deadlines ever again. It just becomes a solvable, highly structured equation. So, looking at your own work, where is the bottleneck hiding in your next big project? Thanks so much for joining me for this explainer, and happy scheduling.